So hi everyone, and welcome to this session, which will be about reinforced concrete design with advanced design. My name is Thibaut Fretet, and together we will see how you can efficiently analyze a concrete structure with advanced design. Then we will see how you can go even deeper in the analysis with the use of the advanced design modules within the advanced design interface. And then we will see that you can also use these design modules as standalone programs to quickly design or verify a concrete member, whether it's a beam, a column, a footing, or even a wall. So this is the building we will be working on. So it's a concrete building with several stories, and it's properly organized in advanced design in systems. With the level property, see, where I can easily hide or display a level. I can organize the elements within the level. That way I have one for slabs, for beams, columns, and walls. So that will be helpful both in the modeling phase but also in the post-processing phase. I will just add a few load cases because at the moment we have dead loads, we have live loads. I will maybe add an extra load case on the roof, and I will apply a live load there. I will define it as a roof category to get the proper combinations. I can also use generators we have in advanced design because we have some for climatic loads, but the building is probably not high enough for the wind loads to have any significance. We also have traffic load, but here I will be using the seismical generator, so I get automatically the 3 directions. I will quickly discard the vertical one because it's well, not mandatory at the Eurocode 8. I will select a region, category, behavior coefficient. You get access to the spectrum, etc. So several various parameters from the Eurocode 8. I will make sure that I'm using the dominant modes in each direction, because for this structure there sure should be dominant modes. I will define the modal analysis that is paired with the seismical cases by defining the active masses, you know, the mass, the building mass that should be excited by in the model, in the seismical analysis. So for sure I will get the entirety of the dead loads, but also a portion of the live loads there, but not the roof load, because you know, due to its combination coefficient, I'm not supposed to take this into account in the active mass for the seismical cases. So and here I will use the Ritz method, which was implemented a couple of years ago, which is way more efficient for seismical analysis, because you can target a participation ratio and you will only compute the mode that are actually relevant in each direction. So we got the load cases. Now I will define some specific combinations, because I expect these combinations to be used not only for the 3D model, but also for in the design module when I will be designing a column, a beam, a wall. You know, you want to use the same combinations, of course. So we have a sophisticated combination generator in advanced design that lets you define combination rules. You see, you can define exclusion between cases. You can force cases all together. Let's assume for some reason you want to like exclude the load case 2 and 3 So you can define your exclusion rule. This will update the matrix. Then for the other combinations, I probably don't need the frequent SLS combination. I will make sure that the new mark combinations are generated because we have several seismical directions. And let's check what we've got. So the first combination will be the new mark ones with one direction and the other with a 30% coefficient. Then I'm getting the ULS combination with load case number 2, then load case number 3, but at no time do I get load cases 2 and 3 acting in the same combination because I've defined an exclusion rule. The SLS combination, and then I'm getting my seismical combinations that involve the new mark combs with the other static loads. Alright, so at this point we are good to go. I will make sure that I'm also using this peak smoothing feature, which is useful when you have columns connecting to a slab, which is the case there. For example, I have a fat slab, so in order not to get the peak forces, the concentration of forces, I will activate this option, and I will run the calculation. So once the calculation is over, you of course get access to the finite element results, and you can check the displacement forces for any given load case or combination. The seismical ones, the static ones. You can check that the seismical analysis was properly performed because you get all the useful information about modes in the reports. But this is not actually the point of today's presentation. We're here to focus on element reinforcement, so we will do just that, starting with a column, for example, like on this level. And you know how in Advanced Design you can perform a quick and basic Eurocode 2 design either on the whole model or on a selection of elements. The concrete design will be conducted with the following assumptions defined in element properties like steel ductility, concrete cover, and so on. You get only the basic Eurocode 2 parameters. And it's very quick, it's almost instant, and you get access to a reinforcement preview. You know which longitudinal bars you need, so I need a mix of 20 millimeter bars, the red dots in the corners, mixed with 16 millimeter bars along the sides. I get the same information for transverse bars. I know the diameter and their spacing, but that's pretty much the only information I have. And if I need to know more, and if I need even a reinforcement drawing of the element, this is when I would use the Advanced Design module. So now I will open this element with the appropriate Advanced Design module, so that will be the column module. But here I'm still in the Advanced Design interface. All I did is it automatically switched to the design section of the pilot for the column that I'm focusing on. And I'm in the ribbon, and I'm set on a new part, a new tab, which is specific to the design module that I'm in. And all the information about the geometry, 40 by 40 square column, is coming from the Advanced Design 3D model. I can find it there. Everything about the material is coming also from the Advanced Design module, and the few concrete assumptions that I had there. But in the module, I'll have way more options and possibilities to actually drive the reinforcement. See, I can ask for the minimum number of bars, or maybe I don't mind how many bars I'm getting, but I just want the diameters to be as small as possible. So you get all these options, even for the starter bars on the top of the column, at the bottom of the column. In the load combination, you can see that the internal forces were coming from the Advanced Design module, so the axial force, the bending moments, and the transverse forces for the static cases. And the combinations will be actually generated when I run the calculation, which is actually not what I would prefer in this very case, because if you remember in Advanced Design, I had defined some specific combination rules to exclude some load cases. So in such a case, what you would need is to make sure that both Advanced Design and the design modules are working on the exact same combinations. You see, so you don't want to export just the load cases, but you want also to export the list of combinations. And when you do that, so I will make sure that I'm starting from a clean slate. You see, when doing that, you're not just exporting the internal forces from the separate load cases, you're also importing the list of combinations. So I'm getting my Newmark combinations, I'm also getting my rules between load case, let me see, and the ULS. I'm looking for ULS combinations with, it's right there. I see I'm getting my ULS combinations with load case 2 and then with load case 3, but I'm not getting load cases 2 and 3 at the same time, so I'm still using the same combination, the exclusion rule that I've defined, and then I'm getting the seismical combination. So see, this will transfer the list of combinations from the 3D model to the Advanced Design module. And when you run the calculation, you see you get the reinforcement, but you're getting also a message here about the ductility class that I'm using. And in fact, I'm probably set on class ductility class A, which is not allowed because we have a seismical column. So if I were to change that for the current column, I would go in the design settings and change this parameter. But in order to avoid doing that for every column that I will be working on, it would be much wiser to make this change at the root, which means on the 3D model. And I can do that in Advanced Design either by selecting the current column or all columns and change this parameter. Or you can also define what is called in Advanced Design, you can create a design template for your seismical columns where you will select class B, and then I will distribute this design template within the model. See, and when you do that, the concrete assumptions are automatically grayed out to ensure that you don't change any of them by accident. See, it's set on class B and it's grayed out, so if you want to modify that, you have to go and modify them in the design template. So this is some kind of a security. It's more secure that way, and this design template is actually an XML file that you can export and share with your colleagues and use in future projects to make sure that you all use the same assumptions. when designing concrete members. Alright, so now if I export the column again, you will see that it's using the same combinations, and I should no longer get the message about the ductility class because I will be set on class B as per the assumptions from the design template. So this will open the concrete, the column module. In fact, I'm set on class B, and if I run the calculation, actually I don't have anything to modify there. The reinforcement is right from immediately correct. So if I were to change anything in the reinforcement, I wouldn't need to go through extensive dialogues. You can just identify a reinforcement object. So here I'm on the transverse reinforcement in the critical zone at the bottom, and I can double click an object, and this will open the corresponding dialog at the right place. See, I'm ready to modify the main transverse reinforcement, package 1 being the bottom, package 3 being should be the top of the column there, and package 2 being the middle. So from there I could change the diameter, I could change the spacing if I intended to, and this will immediately update the provided reinforcement. It would also perform an extra verification and update the warning messages if needed. From there you can check the interaction curves, especially when you have a column with bending moments. See, you get the resulting forces for the ULS, the seismical combinations, and of course the module is checking that the resulting forces are within the envelopes determined by the concrete section with the reinforcement set in place. You get access to diagrams, and of course you can ask for a reinforcement drawing of the element with various views. You will get a side view and section cuts that you can position. You can change their scale as well, and you can easily move the views. Right there, so you're getting a bar schedule, bar marks. I believe now you can even add some information to display some like change the annotation. And that way you will get not only the bar marks but also some information about the diameters. And of course this is what we call an interactive drawing, which means if I were to modify any reinforcement there, you see I have 20 millimeter bars. If I were to change that for changing the diameters, 25. As soon as I close, the report will be updated, and the bar schedule will be also updated. But I'm keeping but it also kept the changes that I made, like the scale. I'm not back on a 1/5 scale. It kept the changes that I had just made. Alright, so that's for a column. Now I guess we can focus on a different element, like a beam, for example. Okay, so now let's switch to a beam from a different level. Let's pick this one, and we will check like this continuous beam. So again, in Advanced Design, you can perform a quick Eurocode to check. Here, and that will give you so it's quick, but it's not basic, because this will return, it will be based on the internal forces that we've got there for various slot cases. You see we've got the bending moment diagram, and the Eurocode to check that we've performed and that only took like 1 second is giving you the reinforcement diagram, you know, the required reinforcement diagram, but also you will get like the provided reinforcement diagram longitudinally, but also the transverse distribution. And we go as far, it's far from being basic, because we go as far as returning steel stresses, concrete stresses, even the cracking, the crack opening width here that I can display maybe as values, like there, compared to the limit of 0.3. For this beam, we even get the concrete deflection, and I'm really talking about concrete deflection and not just finite element displacement, because Advanced Design is able to perform a first calculation sequence to get the reinforcement of the element, and from that it can find out the cracked inertia coefficient. Then it will perform a second loop with the cracked inertia and with the Young's modulus affected by the creep coefficient, and this is how it's able to return the concrete deflection on a beam, but also on a slab. And you even get some reinforcement preview for each span. Span 1, where you can see the longitudinal reinforcement as well as a transverse distribution on the element. What you don't get are some very specific checks, like some, you know, the calculation of the anchorage length or the verification on supports, like the strut verification. So if you want to go that deep, and if you need a reinforcement drawing as well, again, this is when you need the Advanced Design module. So I will open the element within the Advanced Design interface, and this will switch to the Design tab, to the Design module section of the ribbon, where I will get the multi-span, the continuous beam that I'm studying. So again, the data is coming from Advanced Design. There I get many more options to actually drive the reinforcement. I can, for example, take into account the assembly bars in the design. This will be helpful because when you have a beam subjected to uplift forces due to the seismical cases, you got options to help with the anchorage verification. And from there you can run the calculation. This will give us the required reinforcement here. So I guess I will modify the visibility settings to make sure that all bar families are activated. So see, you get longitudinal bars, transverse bars, but we've also got some messages. Sometimes provided reinforcement is slightly below the required one. So this is something you see in the message. This is something we will also notice on the reinforcement diagrams. So I was getting a message like that at the on span 1 and also on span 4, and this is something I can see there. In fact, at the very end for the top reinforcement, the provided diagram is slightly below the required one. And you see also on the first inner support, I'm also below the required reinforcement. So this is something the module will usually avoid these issues, but it's very hard to fix, to have everything automatically correct for such detailed checks. But it seems something you can easily fix with a user operation if you know what to do. For example, here you can just select or identify the corresponding reinforcement object and double click it and make a modification. You can extend the bar. You can, of course, the most straightforward solution would be to increase the diameter, and as soon as you update, the reinforcement diagram gets updated and the warning message is no longer relevant. But sometimes you can do something a bit more like clever, let's say, because if you sometimes all you need to do is just to extend the bar a tiny bit. You see, if we check the first inner support, we can instead of increasing the diameter like we've just done, we could just extend the bar a little, and we will see the impact on the reinforcement diagram if I were to display the first inner support. As soon as I click OK, the model will get updated, and you see this could increase the reinforcement, the provided reinforcement on support. So you can also check the stresses diagrams. You get the support verification, which features the strut verification that I mentioned earlier, and that I will actually show you in a report to show the level of detail that you get in the detail report. So I will actually focus on this chapter, and I will generate the report, show you what I'm talking about. And in the report, you see for this strut verification, see, first you're given the exact article reference from the Eurocode 2, so you know which formula were used, and you know about every single parameter involved. You know how much was the support reaction, you know about the strut width, and if you go on the next page, you actually see how the strut width was computed. You see it involved the inclination of the strut, and you will find some detail a bit later right there. You know how the strut angle, where the strut angle is coming from. You know how the distance from the bottom of the beam to the center of gravity of the bottom reinforcement was computed. It's very accurate. You get the concrete cover, the diameter of the transverse bars, and half the diameter of the bottom bars plus the splice. And you get every information you need up to or leading to the final results with the compressive stress in the inclined strut compared to the limit based on the concrete resistance. And this is important to have so many details in the at least in the detailed version of the report, because sometimes in the past, we were getting questions from users asking for the exact value that we were considering. So now you don't even need to contact us. You get all the information information you're looking for in the report. It's completely transparent. And this makes like checking the manual calculation verification way easier now. And this level of detail, you would not only have it in the beam module, but you will get it in all the advanced design modules, whether it's a beam, a column, for footings and walls as well. So now back to the module, so I can show you the interactive drawing. So you get a drawing with several sheets. You get one sheet per span. So you get the first span with the section cuts and the bar schedule, down to the last span. And in the latest version, we even made it possible to place some text, anywhere on the drawing. You can place an annotation. You can, of course, change the text. You can change the font, and the text will stick. You see, even after you make some modifications on the drawing. See, if you were to change the reinforcement diameter from 10 to 12, see, the drawing will get updated, but the text will remain. See, this annotation will only be removed if you decide to remove it. So this was a high request from our users, because sometimes they would place some text, and as soon as we would make a modification, the text would be gone. Now the text is here to stay. Alright, so that's it for beam. Now we can move on to different member, probably a footing. So back to our model, I can now focus on a footing. So I will select this one, and I will open it with the appropriate design module. So that will be the footing module. So again, I'm still in the advanced design interface, but I get all the information, all the options related to footing design now. So everything about the geometry is coming from the advanced design model. The only information that was not defined is for footings is actually a major assumption. It's about the soil layers. See, and because this information is not known, the module is starting with very conservative soil characteristics. So first thing I would do is modify the soil profile there, and that way I would ensure that the seismical bearing capacity is properly activated, because I have a seismic footing. So and instead of modifying the soil profile for every single footing that I will be working on, again I will make sure to make the change once and for all, and to save this new set of assumptions as a design template to be used by the module. And that way, if I go back to the model, I can assign this module template to all the footings, and that way, even if I start from a clean slate and I export again the footing, it will start with proper soil layers, not the poor quality soil that I had before. Everything else is as defined in the module template. We can review the assumption that we have. For bearing capacity, you can either impose the bearing capacity, or you can have it computed automatically. You can define the crack opening limits, and I can run footing presizing. So the footing is 145 by 155. It's 35 centimeters high. It was reinforced, but then at the end of the design, the module performed the crack width verification. It's a verification once the provided reinforcement is put in place, and sometimes the crack width verification might be failed, not by much. You see, the limit is 0.3 for the exposure class that I'm set on, and the current value is 0.32 or 0.31 in the other direction. So if you can easily fix that, because again it's completely interactive. You can select and click on the reinforcement object, here the bottom bars in each direction, and you can just increase the quantity in each direction. And as soon as you press OK, it performs a verification of the updated model, and the message are now gone because they are no longer relevant. So for footing, you can also check the bearing capacity under the footing for fundamental ULS, but it's usually critical for the characteristic SLS. Can check the stability, so that would be the eccentricity checks and the sliding checks for in a seismical situation, and of course you get access to a reinforcement to an interactive drawing with various views, bar schedule, just like we did, and again it's a completely interactive drawing. Like as soon as I modify a diameter, drawing and bar schedule will be updated. Alright, so that's it for a footing. We may now switch to a different member, a wall for example. So we may now study a wall, a seismical wall. So I will begin with an isolated wall, this one that I will open with the appropriate design module. So again, we are getting the geometry and I guess also the seismical assumptions from the 3D model. Yeah, again, I should change the steel ductility class or create a design template. In the reinforcement settings, I can decide to reinforce the wall with bars or with fabrics. And when I run the calculation, see, I'm getting the main bars and also the end stiffeners on at the edges of the wall, because the wall is subjected to you have an in-plane moment that is taken by the edge stiffener. So I can hover over the reinforcement object. In fact, we have the usual 4 bars with 12 diameters. So the module is checking also the interaction curves, and I can get a reinforcement drawing. So again, several views. You get a single sheet for the wall, and yeah. So it can be reinforced by bars or by fabrics. So this is for a single wall. But as you know, in advanced design, you can also design wall groups. So this is advised when you have, for example, here, several walls in this system right here that I've placed in the common system where I activated the wall group property. So these walls are designed as a wall group. So advanced design is computing a set of resulting forces for the entire group. You get the vertical force, you get the shear forces for the seismical cases and combination. And when you export this group to the design module, so first you get the entire geometry, so you don't have to input manually to define each individual wall. It's all carried over from the advanced design model. I will just check my reinforced concrete assumptions again. And what I want to point out is you are not only getting the internal forces of each individual wall. You see wall 1, 2, 3, and they get highlighted down to the sixth wall, but you also get the resulting forces for the group. And what the calculation does in case of a wall group is that first each wall would be designed individually. So you will see the main bars and the edge stiffeners at the end of each wall, but then the module will perform a verification with the interaction curves for the wall group, ensuring that the resulting forces are within the envelope. So that's it for walls. Now we can check how it goes for when it comes to reinforcing a slab. Okay, so back to our model. Let's work now on a slab. So I will select a slab from this level, I guess, because it's actually a fat slab which is supported by columns. So I intend to design this slab according to the to Annex I from the Eurocode 2, you know, where the slab is divided in strips, and each strip is designed as a continuous beam. So here I have a 3-span slab, and in the other direction to 2-span slab. So I will open it with the design module. This time it will be the slab module. And when in the slab module, see, getting the slab, the supports. So I will use the strip method, which is advised to design a fat slab. In the design settings, well, everything is carried over from the 3D model. I can, check the reinforcement assumptions and reinforce the slab either with bars or fabrics or a mix of two. You can influence the minimum reinforcement. And in the strip tab, I will let the module divide the slab into strips. Right there. So the width of each strip is computed by the module. It's based on the effective length of each span. I have around 6 meters between columns in what they call the minor direction. Here you have a major, minor. So I will focus on the long side. So I have 6 meters between column approximately. So each strip will be half that length, so it will be around 3 meters for the what they call the column strip and then the middle strip. And Advanced Design will integrate the forces along each strip and consider the strip as a continuous beam. So if I were to, let's check the ULS with dead and live load there, I will focus on the bending moment along the beam. See, and for this column strip, for example, I'm getting both. I'm getting a negative moment on the, which is maximum on the first inner support, just as expected. So that is the what they call in Annex I the hugging moment. And in this middle strip there, I get a significant, this time positive moment, where you have tension at the bottom part. So they call that the sagging moment. And based on these moments, when I run the calculation, the Advanced Design module will compute a required reinforcement area as well as a provided reinforcement with bars as per the settings I chose. So in the reinforcement diagram, I can double click on a given strip and see well, the top reinforcement. So blue will be the required and the red being the provided, and here I get the required and provided reinforcement at the bottom face of the slab. So I can now check for each direction. So the long direction there, I can double click on a zone and check that the Advanced Design put 12mm bars with a 15 centimeter spacing to achieve the required reinforcement. And there in this different zone, it used smaller bars because the required reinforcement was in fact a bit smaller. And now I can ask for well, an interactive drawing, and this time I will get two separate sheets, one for top reinforcement, one for bottom, and the other one for top reinforcement. You know, here with the bar schedule. So completely interactive drawing. You can modify a bar distribution. See, because you have some snap points there. There are also options where you can decide to display either the first bar in the distribution or the middle ones. I cannot remember where it was. Bar representation, yeah. You can decide to show only, when you have a bar distribution, only the middle bar, or the first one, or the first and the final one. So you can definitely customize the interactive drawing. So let's get back to the model. And of course, all these design modules that we've seen work in combination with Advanced Design, they can also work as standalone programs. See, you can open the beam module or the column, footing or wall one, and in just a few clicks you will be able to design or to verify a concrete member. You will start from the default element or the one you've chosen for in your template, and you can double click it to modify its length, its section. For example, recently we had to verify a very long beam which was in fact a T-section. So you can have the module automatically find out the effective width of the T-section. It was a beam that featured an opening, so you can add one. In our case, it was 5.5 meters from the face, the inner face of the left support. It was 25 centimeters from the bottom. It was 40 centimeters long and just 20 centimeters high. So you see the opening there on the various views. You can add load cases, so you get access to even water load cases if you're dealing with an underground structure. But here I will do with the usual dead loads and live loads. So in our case we had a 6-8 for dead loads and just 6 for live loads along the beam. Alright, so you will get all the options that we've seen before. You even have one to perform an accurate calculation of the effective depth, which can help reduce reinforcement. And from there you can run the calculation, and you see instantly you get well, the provided reinforcement, including the opening. You can adjust visibility settings if you want to maybe hide for a moment the transverse reinforcement. And you see, if we look at the opening, we have a top lintel which is mostly in compression, so you don't need much extra reinforcement there. But the bottom lintel was in fact in tension, especially in its bottom part. But because we had already some significant reinforcement from in the bottom part of the beam, we just needed an extra layer with 5 bars with a 10 millimeter diameter. And you can move on the view to actually see the reinforcement in the lintel. And at the end of the design, the module is performing the required stress check. Here it is exceeded, and if you want to fix that, you can simply well, modify the diameters like we've done before. You can update the bar length to get the proper anchorage calculation. You see it's also performing a new verification based on the updated reinforcement, and the warnings that I had are irrelevant now with the new provided reinforcement, so they are no longer returned. And from there you can check the other results. We've seen support verification and down to the interactive drawing of the beam with the elevation and the section cuts and the bar schedule. Alright, so I hope I kept you interested. Together we've seen how you could design a concrete structure and go real deep in the analysis and produce drawings with the advanced design modules, either in combination with advanced design or as standalone programs. And now we might have just a few minutes for questions if you have any. Else, well, feel free to send me an email at any time.